The good customs of the department are that when one of our own members is the seminar speaker, they don't need an especially lengthy introduction. So I will just turn you over to Larry Paulson, who is going to be telling us about security protocols and their correctness. Thank you.
Is that on? Yes, that's better. Yes, I decided to turn up for this Wednesday seminar at least. I chose the title of this with some care because normally when you prove a thing about computers, you pretty much know what it means to be correct. So if you got a thing for taking the square root, say, you know what a square root is, and it's correct if given an input which is presumably a positive number, and it yields something which is sufficiently close to having the property that when you square it, you get back what you started with. Okay, I stumbled a little there, and that goes to show that even for a trivial thing like square root, it can be non-trivial to say what it means to be correct, but it's still not that non-trivial. But when you get to security protocols, you get people arguing desperately that something is correct and no it's not, and yes it is and no it's not. And the thing is, often no one really knows what the protocol is meant to do in the first place. And that is one reason why proving their correctness is even harder than this usual sort of exercise. Now, just to try and motivate this, and I am really starting at the very beginning, so if you are an expert on DES or something, I'm sorry, this will be a little slow for you. Right. Here we have our classic example, and in case you don't know, this lady here is Alice, a gentleman over there named Bob, and this nasty villain there is named Charlie. And the point is that Alice and Bob would like to hold some kind of intimate conversation without this person hearing it and perhaps having it appear on tomorrow's Sun. So somehow, well, I mean, there are lots of things they could want. The first thing I suggested was they might want to have secrets that this person doesn't know about. That isn't the only thing they would want, however. You see, if this is an email message, if they're communicating by email, it's quite easy for some interloper there to insert a not somewhere in a message and leave it otherwise the same. Then the person receiving it will get this message with a not in it and be deceived because clearly not can change the meaning of things, and yet the rest of the style is exactly the style that this person would write, and so he would believe that it came from Alice because it sounds exactly like Alice, and Alice has said the very opposite of what he was hoping. So I suppose I should start using a little jargon here. The kinds of things we want are, I'm getting ahead of myself slightly, authenticity, which means that if you get a message, then the message that you get is exactly the message that was sent, and it was from exactly the person you thought it came from. And underneath that, secrecy, which is that if you send a message, it will get to exactly the people who you wanted to get it and not to anybody else. Now, of course, when one notes that networks are insecure in this way, the thing everyone says is, oh, use cryptography and all the problems are solved. Well, of course, the whole lecture here is about how that doesn't necessarily solve all the problems. People often also say, use public key cryptography and your problems are always solved. And because they say that, I chose today to look at a public key protocol that's broken and show you how a public key cryptography doesn't solve all the problems. Indeed, I am actually going to ignore a whole set of problems in this lecture, but I assume everyone has a rough idea what public key cryptography is. Everyone knows one key. They send you a message encrypted with that key. No one can read it, but you can. So it's all very clever. But you see, there's nothing to stop this person here from announcing to all the world, hi, my name is Alice, and this is my public key. And of course, the key that he transmits isn't Alice's key at all, but his key. And then anyone might be fooled and send intimate details encrypted with Alice's key, hoping that only Alice will read them, when in fact it's not Alice's key at all, but his, and he will read them instead. So that gets into the whole question of key management and so on, which I'm not talking about today, but Even if everything that I did today was perfectly sound, there are lots of other problems one can worry about. So it's a very complex business. Right. So anyway, can cryptography make networks secure? Well, I think it can, but let's talk about that. I mentioned wanting your messages to be authentic and to be secret. Authentic also means not tampered with. Now, one thing that makes security a more difficult subject than square roots is that normally if you call a square root routine, it's because you want to take the square root of something. You don't actually call a square root routine with the intent of making your computer fall over. On the other hand, in any security situation, you have to assume that there is someone out there who will do anything he can to cause mayhem. And how can we say what this enemy can do? You know, he might think of something we've never dreamt of. So one needs to actually model, somehow you take worst case assumptions and think of an attacker that has almost unlimited and unimaginable powers and assume that such a person is there. And of course, if when we have modeled this attacker, we have left out something, then of course we will miss some attacks. The other thing is, no matter how powerful you make this attacker, I found, at least in my work, that isn't good enough, because if you assume everyone else behaves perfectly and never makes a mistake, then you can formally prove some very unrealistic properties which basically say that this very powerful attacker never learns anything at all. And so you can prove all your theorems very easily by appealing to these powerful and quite unrealistic results. So what you need is to say, not only do we have a powerful attacker, but the other people, the honest people, occasionally goop. They occasionally leak information out, so they occasionally will throw away a key. And now you have a compromised system. Now you can't just say that the attacker doesn't know anything. Suddenly the attacker's got loads and loads of stuff to work with. And the question is then still, in a situation where some of your agents maybe are under an attacker's control and anybody might occasionally give away something, can we still prove anything about the parts of the system that are still uncompromised? And in fact, the answer is yes, one can. A last point about the model is I don't assume that ciphers are being broken. Sometimes people think this is a crazy thing because, of course, ciphers do get broken. But here I appeal to the old principle of separation of concerns, which is there are some people out there who are very good at making ciphers and defeating attempts at breaking them, and other people who are working at the protocol level. And certainly if your protocol can be broken without breaking ciphers, then it is certainly a pretty bad protocol. So we first make a protocol that is safe, assuming the encryption itself is perfect. And if we have that, then we can look at the encryption level and see if that's done properly. This is quite important, in fact, because I, last year, managed to prove, once I just proved quite definitively, I thought, the correctness of a protocol, only to find the published version of it was utterly broken. And the thing is that the published version had gone a further step and described how the encryption would be done and prescribed a method of encryption that was utterly broken and basically then collapsed the whole protocol. In case any of you know about security, I can briefly say what they did wrong. They were doing encryption by a sort of one-time pad and using their one-time pad twice. Right. Now a little notation here, both to let me talk about what's happening next and also to put you in the picture about the kind of concepts we'll be using. Okay, so in these protocols, people like Alice and Bob will exchange messages. Oh, I should say, what is this S person doing over there? Actually, I don't need S today, but often you do need S. S is called an authentication server or a trusted third party, and there are a number of protocols in which you have a person here, someone that you absolutely trust, someone like Bill Clinton, say, who Alice, say, being, I forget what her real name is, but I'm sure you know, wanting to send an intimate message to someone, goes to this trusted person and says, I need a key which only Bob will know and not anyone else. And so, assuming you can trust this person, then there are protocols that function in that way. Anyway, so we have Alice and Bob, who, of course, we will normally call as A and B. And we have things like nonces. Now, what is a nonce? If you look in the dictionary, it says a word, something like a word chosen just for use now, something like that. And what the point about nonces can be explained by, there's one of these tales from the Arabian Nights, in which Ali Baba sees he's hiding somewhere, some caves, some thieves walk up to a rock somewhere, and they say, open sesame, the rock rolls away and there's a cave. The thieves go and take gold out or something, and then they go away. Now, Ali Baba goes up to this cave, and he says, open sesame, and lo and behold, the rock rolls away again, and in he goes, and so on with the story. So this cave was the security interface to this cave was very poor. There were no nonces in there. And so Ali Baba was able to replay the same thing that opened the cave once, worked again to open the cave. What normally one does, now this story doesn't quite work very well, but you really would need the cave to challenge whoever's asking to open it. So you say, open sesame, and the cave says, what's your mother-in-law's middle name? And then the thief could answer a question like that, so he does, and then the cave lets him in. Then Ali Baba tries the same thing, open sesame, the cave says, what did you have for breakfast? Well, Ali Baba doesn't know what the thief had for breakfast, and so the cave won't let him in. Now, that doesn't quite fit with what a nonce is. And nonces are a little less elaborate than that. But when you are sending messages around, which are indeed strictly analogous to open sesame, you put a number in, and every time you run the protocol, you put a different number in. So if some Ali Baba who's been eavesdropping sends an old message out, and it has an old number in it, then the receiver will know that it has an old number and just chuck it out. Right, that's a nonce. Key, okay, I assume you all know what a crypto key is. Now this is a notation for encryption. X is the message you want to send, and you encrypt it. And here I'm only talking about public key encryption today. You know Alice's public key, and I assume for the moment that you really know Alice's true public key. You want to send X to Alice, and so you encrypt using standard encryption algorithm, and you get this thing. So anyone can form such encryptions, but only Alice, so this thing will be floating around the network. Everyone can see it. Anyone could say such a thing, but only Alice can look inside and get X out again. And now we can look at a very simple security protocol. Oh, and by the way, this Needham is some guy who works at Microsoft. Right? Anyway, the first thing one has to ask is, what is a protocol like this for? And the answer is, I don't know for sure, but if it has one job, then it's correct, and if it has another job, then it's not correct. But this is a typical example of such things. First, so this says Alice sends Bob a message, and that message is something encrypted. It's encrypted with Bob's key, so only Bob can read it. And it basically says, hello, this is Alice, here's a nonce. So it just chooses a random number and sends it to Bob. Now, the next step, if Bob receives such a thing, Bob should reply as follows. He picks his own nonce, NB, packages it with Alice's nonce, encrypts it so that A can read it, and sends it back to A. Now, what's the point of packaging with Alice's nonce? It's just what I was saying about the whole point of nonces, that when Alice sees this thing come back to her and sees inside the very same number that she just chose a moment ago, she will say, right, this must be a reply to my earlier message because this is the first time I used that number. And in real protocols, a nonce like this might be 40 random bytes. So if you've got 40 random bytes, it's pretty unlikely that the other person just guessed that. Okay, now there is a third step in this protocol. Alice, having first sent this message, and then having received this message. Now, of course, Alice won't know that it came from Bob, because in a network you have no idea where messages come from, but you've got it. But Alice has got a message with her nonce in it, the same nonce as she sent, so she says, oh, everything looks okay. So I will reply to Bob, sending his nonce back to him and encrypted so he can see it. That's the protocol, those 3 steps. Now, what does all that do? Well, let's think about all that a little. Look, what happens here? First, Alice encrypts a random number with Bob's public key, and later on she sees that same random number again. The only person in the world who could decrypt that is Bob himself. Even Alice couldn't decrypt that message, even though she formed it. She has no means of decrypting it if she stumbled across it again. So definitely, Bob is around. Similarly for Alice, Bob has chosen this random number NB and encrypted it with Alice's public key, and later on, that same nonce is floating around again. The only person who could have decrypted that is Alice. So Alice is also present. And I never really understand why you merely want to know whether somebody is alive or not, but sometimes that's all you want to know. So if you've got Alice on one part of the world and Bob on the other part of the world, and they run this thing to completion, they both know that the other person is alive and present. But sometimes you want more. Sometimes you want those nonces to be secret as well. And you might think for the moment they are. You see, the point is that this nonce here was protected first by B's public key and then by A's public key. So it looks like it's staying secret. And equally, for Bob's nonce, all the time they're sent only encrypted. So you might think they're secret. Oh, and by the way, what is the point of establishing secrets like that? There are a lot of reasons, but a typical one, there is a standard internet protocol which is used in Netscape. So the next time you order a musical party, which is a way of toilet training a toddler I saw on the web once, when you order a thing like that and send your credit card number, it is actually being protected using a protocol called SSL, and that protocol does an exchange which is, well, something a little bit like this. And when it has arrived at these 2 nonces, NA and NB, which it does manage to make secret, then it scrambles them up and uses that to make a key, which is then protects your credit card number. So a lot of protocols do that, and there are various reasons why you invent new keys all the time. I don't think I need to get into them now. But obviously, if you have this way of inventing keys by exchanging nonces, and if these nonces aren't secret, then your key won't be secret either, and then your protection goes out the window. Now, it turns out these nonces aren't secret. Now, these sorts of attacks can be very difficult to understand, so a little analogy holds. I assume you all know what postal chess is. You play chess by mail. And it's fairly well known that in postal chess you can quite easily hold your own against a grandmaster. All you do is engage to play 2 games with grandmasters. Make sure that with one of them you go first and the other you go second. When you get the move from the first grandmaster, you just send it on to the other grandmaster, and when he replies to that move, you send it to the first one. So both grandmasters think you're playing chess with them when in fact they're playing each other. But one of them is, at best, they will both draw, or one of them will win, so either way you will at least draw with one of the grandmasters, not actually beat one. And of course you're not playing chess at all. And that is how a middle person attack works. Now what has happened here, this diagram is showing you 2 runs of that protocol. What has gone on here is that Alice has, by some act of stupidity, chosen to run this protocol with a bad person, and in doing so, this bad person is able to essentially copy the information that Alice sends to her over to any other person that he chooses, and therefore deceive anyone else in the world into thinking that he himself is Alice. So the effect of this from Bob's point of view, Bob will think that he has run the protocol with Alice, and he will think that he's established secrets with Alice. If he then tries to use those secrets, then this interloper is going to get them all. In a little more detail, what's happening is Alice starts a run. Here, sends her nonce along. Charlie can read it. And again, it all hinges on Alice's having made this dumb mistake in the first place. Charlie can then forward the nonce to Bob, this time because he strips off the encryption that he knows how to read and adds Bob's encryption. Bob's reply he just passes straight back to A. He can't in fact read it and doesn't need to because A will very obligingly decrypt it for him. So he will eventually learn this other nonce, and which he can then encrypt for Bob. So in the course of this run, Charlie will pick up both nonces. And also in the course of this run, Bob will have every reason to believe that he has been talking to Alice. I said this was a subtle subject, and in a sense it is, because I was telling you that if we don't care about secrecy, this protocol is actually all right. The reason it's all right is that if you merely, the weaker thing the protocol always gives you is that the other person is alive. And Bob here, having run this protocol, thinks he's been talking to Alice, and in a sense he has been talking to Alice. Alice is definitely alive, so the protocol does guarantee that first property. The only trouble is, although Alice is alive, someone else has been in on the conversation. Now, I thought I might show you in a little more detail what this attack looks like. I don't think I need to run through again exactly what happens. There's the first honest message. Then this is the second run starting with Charlie. That's Bob's reply to Charlie, which is then he passes on to Alice. You have here the two runs. One is in blue and the other is in red, and so on. So, and by the way, this is called Lowe's attack because it was discovered by Gavin Lowe, who has done a lot of work on using model checking to verify protocols. And he's shown how a model checker can very quickly find attacks such as these. Right, so this is a bad situation. The question is, can we verify protocols? Can we prove them correct? Now, for a long time, the main method of proving protocols correct was based on this band logic, Burroughs, Abadi, and Needham. There's that Microsoft guy there again. This is a strange sort of logic, what they call a logic of belief, rather than an ordinary predicate logic. So you have various special forms of assertion that aren't not immediately clear. It's sort of what they mean intuitively is clear, but what they mean formally is not at all clear. So when you talk about a nonce, often you want a nonce to be fresh. In other words, you want the nonce to be a new one that hasn't been used before. That is actually a relatively concrete property, but in this logic it's a primitive. Less concrete is the notion of a key being good. Well, this is again a primitive of the logic, but to say that a key is good, and often it would be a key is good for use between Alice and Bob, somehow that includes a lot of things, including that the key is fresh and the key is only known to Alice and Bob, and so on. And an even more complex property, but one that's quite crucial, I mentioned this person S, this authentication server, who sometimes appears in protocols. You actually would have in the band logic the notion of certain agents being trusted to do certain things. so that if a certain agent gives out a key, then you are allowed to assume that key is good for Alice and Bob and so on. Now, this was a landmark paper, and this original paper looked at some half dozen or so protocols in great detail and picked up a lot of subtle flaws in them by doing a very, very concise analysis using this logic. However, later people discovered holes in some protocols that, according to this logic, were sound, and a lot of research since has involved patching up the logic, and in the course of patching it up, somehow it got bigger and bigger and bigger until, whereas in the original paper you could prove a protocol with something like writing down 10 lines and you were finished, I saw a thesis which had something like 60 or 70 pages of gigantic derivations to prove some rather simple looking properties. So you see these logics, the attempt at making these logics work better has somehow destroyed their simplicity, which was one of their great advantages, and made them horribly complicated. But anyway, as I said, this is still used somewhat. All right, carrying on a little more. Another method, by state enumeration, that covers a lot of things. It is somehow not too surprising to think of a protocol as some kind of configuration or a set of possible configurations. You somehow model all the people in your system and all the things they can do. You define a notion of a bad state. You search all reachable states and you ask, are any of these bad? And if none of them are bad, then you say it's fine. We had Catherine Meadows here a while ago talking about, she has a rather unusual system which I can't say too much about, but one element of it certainly is doing this kind of search. And there's another tool there by Millen. As I mentioned, Gavin Lowe has started a new strand of research based on model checking, which has been very successful, and there have been, I am sad to say, a very large number of copycat efforts in the States, some of whom have barely bothered to mention that Gavin Lowe even exists, so it was all their own idea. I shouldn't say that, but there it is. Anyway, so there is a huge industry growing up around this approach. And the main advantage of model checking in the way this is being applied is that you can almost literally key in a protocol and press a button, and if there are any obvious attacks, certainly it will come out in seconds, I think, or certainly in at most a couple of minutes. And if there is an attack, it will actually print it out very neatly, or at least it will print out some gobbledygook, which in a shortish amount of time you can work out where the attack was. So that's all pretty good. The main limitation of this is the assumptions required to make the system finite in the first place. These tend to be very highly idealized models, and although one can argue, I know Gavin is quite good at arguing that you can really pare down the population to 3, so you have Alice, Bob, and Charlie, and that's it. You don't really need anyone else. And you might even assume that there are only 2 crypto keys in the world and this sort of thing. And one can give a good story that if there are no attacks under those conditions, then it's fine. But sometimes, at least, one might want to look at a more realistic model and perhaps look at more detailed properties of a protocol. And when it comes to that, in other words, once you don't merely say, I'm looking for attacks, if you say, I want to analyze the protocol and to see what properties it has, then suddenly you need the ability to talk about logical properties and so on, and that you can't easily do in model checking at all. So, I come on to my bit, which is formal proof. Before I do, actually, I have my little sermon on model checking, which I like giving. You see, in the States especially, formal methods now is almost purely model checking, and that is both good and bad. The main good thing about it is that all of a sudden formal logic are being used in all sorts of places where they would never be used before. And the bad thing is that model checking is inherently limited in that you are always looking at finite state systems. And occasionally, people make stronger claims for it than they can do, and it's not so unusual to see that someone checks a finite state system and then pronounces a thing correct, because it's a bit like the prime numbers. You checked 3 is prime, 5 is prime, 7 is prime. Well, they all must be prime. And one does see that kind of reasoning. So what I hope for model checking is that it will get people excited about using logic, and once they get in the habit of using logic, they will look at formal proof as well. And it is a myth that machine proof is always unbearably laborious and slow. It is laborious and slow, but not unbearably so, at least not always. Now then, so at last I'm talking about my own work. I'm modeling protocols inductively. Now, I suppose I need to say a couple of words about what that means. When you look at a protocol, when people are arguing informally to say this protocol is correct, they tend to argue in a certain stylized way. Someone says, this nonce will remain secret, and the other person says, why will it remain secret? And the first one says, well, it can't be secret because it's always encrypted. No one has this key, so they can't decrypt it, therefore it's secret. So the first one says, well, couldn't someone get hold of the key and then decrypt the nonce? Or couldn't someone have sent this other message, thereby causing someone to send this, and then he will get out the nonce? And the first one says, no, the situations are possibly caused, etc., etc., etc. Now, when you do this in English, of course, it's very easy to get muddled up. But this exhaustive analysis and going back to see what can have happened is induction. Induction is basically looking at all finite ways of generating a thing and proving that they all have a property. And so, any protocol, all the things that can happen in a protocol, I will just model as a so-called inductive definition. Oh, by the way, if you are happier with the semantics world, the semantics way of talking about things, I would just say that I give an operational semantics of the network. In other words, you lay out all the people in the network, you describe what each person is allowed to do, and then you ask if they all do the things they're allowed to do. And of course you have the spy in there doing all these bad things that he does. You then see if you can prove that in this particular setup nothing bad can happen. And that is the same thing. Anyway, now the basis of these inductive definitions are fairly concrete. Now here, and this is much like model checking and not at all like belief logics, like the band logic. So instead of having abstract notions like the notion of a key being a good key, one uses very low-level notions like A attempts to send a message to B. Even this is actually subtle because, of course, attempting to send a message doesn't guarantee the message arrives. So somehow in the model, you have to consider the possibility that the message never does arrive. Some people do this by having an entirely separate event, which is Bob receives a message. But I do it slightly differently here. Now, once you have this notion of an event, of an action, then a particular history will just be a list of actions. That's all. So as I said, we have an operational model. In other words, we just model what people can do. In other words, what messages they can send. And you can have interleaving and so on because all these people are there. At any point, any of them are allowed to do certain things. If they do that thing, they send a message. They can all be doing things at the same time, and so you could have many protocol runs being interleaved. Now, what's this algebraic theory? Well, I have another overhead on it. But this is a thing that I do think is novel in my approach. You see, if, I guess cryptanalysts know, spies and so on, if you have intercepted a lot of traffic, you don't throw it away even if you can't read it now, because maybe later you work out ways of reading parts of it, and then when you decrypt those parts that you've just managed to decrypt, you might then in those find more information that you can use to decrypt other things, and so on and so forth. And so you then need to formally model what a spy could do given all the past traffic and, say, given other information that he has. So I have defined some operators for talking about this, and it turns out these operators have a lot of quite strong properties which you can use to simplify the expressions that arise in these proofs. Now, of course, you need to model an attacker, and this is another quite difficult thing. What one normally assumes, one assumes an active attacker. In other words, this person is not merely listening, but actually actively tampering with messages, sending them out, saving a message from one run, and maybe cutting it in half, and then joining it together and sending it out later, and so on. One difficulty with that for model checking people is that that is an infinite behavior. The attacker can do any combination of old messages and put them together in any crazy way and send it out. Now, that causes no problem for me, and so it is quite easy in the formal proof world to have to describe this behavior as a single rule, in fact, and just add it to your definition and have the same attacker in every protocol you look at. So naturally, if the attacker is always the same, specified in the same way, it simplifies things. Certainly in early model checking work, it was necessary to look at what messages that an attacker could send could possibly do any damage and restrict the attacker to only send this very restricted class of messages that looked damaging to you. Then, of course, there's the worry that, well, maybe you left out some damaging messages. Now, recently, Gavin Lowe and Bill Roscoe have found a very ingenious way of not having to do that anymore, which I never quite understood in detail. But it is a problem, this anyway. And finally, don't want to sell my own work, but there it is. In case you haven't heard of Isabelle, it's a system I've had something to do with, although, by the way, I'm not the only developer. There's a group in Munich which is doing, if anything, most of the Isabelle development these days. It's quite easy for me to say that Isabelle is the best system for doing this particular work for the simple reason that everything is completely tailored to Isabelle, and it would actually be very surprising if Isabelle weren't the best system for doing it. Whether it can be done in some different and equivalent way in some other system, of course, is an open question. Anyway, thought I should say a few words about this algebraic theory of messages that I was talking about. These three operators, they actually of some basic fundamental importance. It turns out they are not only useful in specification, they're also useful in telling you what kind of thing you've just proved. They're all very, very simple. The notion of parts, I hope, is perfectly obvious. If you've got a lot of traffic, just imagine what are all the parts of that traffic. And by parts, of course, I mean you have some notion of a message not as a string of bits, but as high-level things like names of agents, crypto keys, nonces, that kind of thing. So if you just imagine that if you have a set of messages gathering up all their subcomponents into a big set, then that's what parts refers to. And this little thing on the right, by the way, is just to remind you that if you have an encrypted message, I regard the body of that message as always being a part of it, even if we don't know how to read that message. Now, what is the point of having this operator? Well, one can prove a certain class of theorems which says that certain things never ever are generated at all, and such theorems are expressed using parts. So if you want to say, for example, that no one ever sends out their private key, then I can state that no one's private key is a part of a message history. And then, assuming I can prove that, then I'm done. And the point is that this, because it has such a simple definition, is very easy to reason about. Now, I call this sort of thing a regularity property because it's not asking who can read the key, but it's saying the key just isn't sent at all. Next thing down is this analyze operator. Analyze is almost the same thing as parts, but whereas parts is just all the components, whether you can read them or not, analyzes all the components that you can actually decrypt. So it's the same as parts, except that if there's an encrypted message in there, then you only get at the body if you've got the right key. Once you have this operator, you can now express properties which concern a secret which maybe Bob can read but Alice can't. Or you can now talk about secrecy. Finally, going in the other direction, one has to worry about here the spy in his role as inventing new messages by taking apart bits of old ones and joining them together. So this is again a very simple operator in which basically you imagine taking chunks that you have and joining them to make messages. These are also defined inductively. It turns out it's very easy to define them in that way and very easy to prove things about them. I have here a few examples of the laws they satisfy. They satisfy quite a few more, incidentally. But just to give you a flavor of it, for example, this first one says that if you've got a lot of messages and you take the parts of them, and the parts includes all the original components, if you take the parts, and then if you take the parts all over again, well, you're learning nothing new because you took all the parts the first time. So that's a fairly obvious thing you'd like to have. Slightly more obscure is that if the first time round you use analyze and only get at the parts which you can actually read, and then if you take the parts of that, you get all the parts. A rather more interesting one is this, and this is a little puzzling at first. It's not too difficult, really. This one says, if you've got a lot of traffic, and if, the synth here means, if from this traffic you build up, you invent loads of new messages, and then go down and decrypt everything you can from those messages you've just invented, somehow it's obvious that if you're going to invent new messages, you haven't really got anything new from before. And indeed, this theorem says that it would be just the same thing to separately go up and go down and not bother to go up and then go down. Now, the point about having laws like these, never mind if you didn't quite follow that one, is that we can simplify very drastically the expressions that arise involving these, and you often do get these quite deeply nested. But thanks to the simplification, they never end up being nested more than 2 deep, and the reason they're nested 2 deep is that there are certain combinations like this one in which I believe there are no such equations. It's a bit like modal logic, if you know that sort of thing, where you have all these boxes and diamonds, and you can imagine long strings of boxes and diamonds, but nearly all of them collapse down into almost nothing. This, by the way, is a thing which I think is particularly important, that one has these operators and that you have laws about them, and that they are expressed all in terms of sets. So you see, this is talking about a set of components, and it yields a set of components. Most other work, even using formal proof, has not used sets, and instead talked about, say, a relation, like the relation of a certain component being derivable from other messages. Now, that may seem like a minor point, but in fact, if you express it as a relation, then you lose all the innate equations, and then you can't use a simplifier anymore, and then your proofs have got 10 times longer than they were before. And these proofs are jolly long already, so if you make them 10 times longer, you're sunk. Also, that having them as 3 separate notions, what one normally sees is to have them all bundled up into one gigantic operator, which, well, typically doesn't involve parts at all, so people don't bother with parts, which is a shame because it's a very easy thing to reason about. They take the other 2 and they use this combination here of the building up of the breaking down, which is what the spy does. You know, he analyzes messages and then he invents things. But this is a very cumbersome thing to work with. So it's clearly a mistake to do it in that way. UTO. Should just say a few words about what it looks like to specify a protocol. And I guess in doing this, maybe I should find the original protocol and just, oh dear, remind you what it looked like, sort of. Let's see if he can find it. Must be here somewhere. Oops. Yes, at last. Remember, we had these three messages. Now here, this bit of gobbledygook is modeling the second message. And when you model it, of course, you've got to be as realistic as you can. What is meant to happen, of course, when you write a protocol in this way, and here I am talking about this message here, Bob only sends this message because he's received that message. And, of course, when Bob receives that message, he doesn't know it came from Alice because you never know where things came from in a network. So all that Bob knows for sure is he got that. And if he gets that, then he might send this. Now I say he might not, he might be down at the moment or something of that sort. He might have had some buffer overflow and he might have lost that message and so on. But if he wants, if he is able to, he can send that message. So the inductive definition will have the logical equivalent of this bit of English here. So, and this bit of English is giving the conditions under which that rule can fire. So if the current history has the following event. Now this event refers to message 1. So it says, somebody said, I call it A prime because I'm not pretending we know it's from A. Somebody said to B this, and this is just formal notation for the first message. Someone sent that first message to B. So if that event is there, and if B has chosen a nonce which is fresh, by fresh I merely mean this nonce doesn't exist anywhere else in the trace. Then this event can occur, and this event corresponds to Bob sending to Alice that message there. Now, there is a very tricky thing buried in this, but a very important one. Messages aren't always received. So the mere sending of this message doesn't guarantee that Bob will ever get it, and so it doesn't guarantee that this message will ever be sent. The thing is, I don't actually need to put that in the model at all. The reason I don't is that nothing ever forces these rules to be triggered anyway. Even if Alice did send this message here, there will still be traces in which this message is never sent because there's nothing in the model that forces it to be sent. And if it happens not to be sent, then we can regard this as saying this message never arrived. So that kind of thing, rather than adding a whole separate event to the model which corresponds to a message being intercepted, that notion is in the model anyway, and so it's that much simpler for not having to put it in explicitly. Take this away, I suppose. Now, very important, I mentioned the spy is present, and here is how we always model the spy. You put in this, oh, by the way, I don't think I said very clearly, a protocol specification will include this for round 2 of the protocol, and something very similar for round 3, and actually something a lot simpler for round 1, because round 1 is not replying to something else. But it also needs a couple of other things, and for a start we need to build in an enemy. And if, as usual, we assume an active attacker, then we put in this rule. And this bit of logic basically says, if X is any message that could be invented from anything that could be extracted from anything that has ever been said in the network, in other words, someone has tapped everything and done every possible thing to it, then that message, the spy could send that message to anybody. So that is pretty powerful spy, and certainly a very simple one. The nice thing about this, although it's very powerful, because it's always the same, it is not at all hard to, well, when you prove a thing once, you can package together techniques that will let you prove similar things again, and that has worked pretty well. If I were being honest, I would say that a lot of these proofs were very, very hard to arrive at the first time round, but once you get a body of techniques, you can knock things off in a week sometimes. Accidents, I mentioned this at the very start, that you need to build in a bit of carelessness as well, and the usual thing that I build in is that if there is some secret that the protocol is concerned with, I add as a possibility that that secret is sometimes given away. And then the kind of thing you would like to prove is that, well, of course, if the secret is given away, then it's not secret, and that's pretty trivial. You want to know that other things will still be secret. In other words, that the giving away of one secret doesn't make the whole system collapse like a house of cards. And this sort of thing can be proved. Right. Some examples. Okay, here's a trivial one. Someone's secret key is never lost. I mentioned you express that using the parts operator, and it's really quite trivial to prove for a usual protocol. Another sort of thing, for this kind of protocol in which the honest agents always invent a new nonce, it's sort of obvious that because they always invent a new nonce, if you see a message with that particular nonce in it, there can only be at most one such message, and therefore the presence of the nonce in the message identifies everything else. That is a very strong and very useful property, and one often needs it. And when you say, well, what if these two are the same? Well, if those two nonces are the same, then everything else is the same, and then perhaps that gives you what you need to prove your theorem. This, again, is relatively straightforward to prove because it's not talking about secrecy. It is just a property of all the traffic, regardless of who can read it. Now, much harder to prove typically is anything that claims that a fact is secret from somebody. Well, we always just prove that things are secret from the spy because we assume everyone else is honest. And for the broken protocol, even then, you can prove that the nonces are secret if you're willing to make other assumptions, like that Alice doesn't make mistakes. There are some rather, I can't go into detail, of course, but all these things are proved in pretty much the same way. You do a big induction over everything that can happen. You simplify using all those rules I showed you. Often, if you're lucky, there'll be almost nothing left. However, sometimes you need to do more logical reasoning, much of which can be automated. And many of these are proved in proof scripts of just 3 or 4 lines, say. So, of course, there are the odd 20-line ones as well. Some of them are very hard. Some of them, and the thing which is actually appealing about this is that the proofs often do relate to the intuitive argument. And in particular, if you have a proof which is very short, like this one, it would correspond directly to the argument that, look at all the rules, no one sends their secret key, therefore it's never lost. When you get a horrible long proof, you can actually follow the reasoning and saying, well, this might have happened, that thing might have been compromised, but if that's compromised, then something else happens. And so you have a thing which can be rendered into English. And this is an advantage of proof over model checking, that a proof gives you reasons, model checking simply says it's okay. All right, time to stop. I've looked at a lot of protocols. I don't think it's necessary to name them all, but most of them are relatively simple, although there's a lot of quite different types of ones here. In fact, there's a protocol I left off the list, a variable length protocol, and those are rather unusual, in fact, and a variable length protocols are particularly hard to analyze because a lot of protocol analysis systems don't even let you specify a variable length protocol. Although most recently I've looked at TLS, which is a rather complicated internet protocol with it has many, many paths through it and lots of optional things. This was the hardest, well, apart from the first ones where I was developing the method. This took 6 weeks to arrive at the proof, although I should say of those 6 weeks, 2 of them were spent trying to decipher the absolutely unintelligible thing that is called a specification, which you get off the internet. It's written in utter gobbledygook. And for that, I actually needed to talk to Martina Badi, who helped to write this, to understand what it all means. But having spent that 2 weeks, it was still quite hard, another 4 weeks just getting to grips with how to even model some of the complicated things this does. The time, this is a bit of a cheat when I say it will run in something like 9 minutes on a computer. That is nice if you need to run the proof all over again, although really, of course, the main thing is getting at the proof in the first place, but at least it means that you're not going to spend ages waiting for a proof. In terms of the human time, well, at least for me, it doesn't usually take too long, but I have to say it's not a very easy method to pick up. But people manage. When I say a few hours or days, by the way, it is perhaps a bit of a cheat. What one can do, what one often does is you have a protocol, you're not happy with it, you say, well, let's change it right here. Then the question is, how much work do you have to do all over again? And the answer is, most of the time, you can just rerun the old proof script, and if your change has been a minor one, then there will be no changes at all to this. So if you, for example, just exchange some components of a message, for example, I would think that most of the time you would not have to change the proof one bit, and it would go through just as before. If you make a more substantive change, you still might get away with using most of the old proof script. And so for this kind of debugging a protocol, it behaves quite well. When you've got a new and horrible one, it can take a very long time. So I don't want to suggest this is easy. I would propose this as a complement to model checking. So I have no intentions of taking over the world. The point about model checking, of course, is that you can do these very quick checks in a protocol. Having done that check, if you would still like to learn more, then you can devote a couple of weeks to analyzing it in this way. Right?
Well, thank you very much indeed. Other people have some questions.
Yes, Mike?
Do you need to add any special things that you do capability to things go smoothly?
I wonder, yes and no. I did spend quite a long time on a new powerful theorem prover. Although I did that, it wasn't necessary. I'd done a lot of proofs. I think I'd done the whole half dozen or so protocols, and then decided it might be neat if I spent some time making a very fast prover, which would be another talk. I can't think offhand of anything that had to be put in just to make this work. I could say, though, that there are certain features which, if you say wanted to use some other system, that other system will need to have certain features or you'll be hopeless. It certainly needs a simplifier. And it also, one often gets if-then-else type case splits. So very often you have an encrypted message and you then have to ask, is this key broken or not? And then you get two cases and it splits and splits. Now, if your system will do all those splits for you, it will be easy. If not, it will take you a very long time to get through all the cases.
Do you agree that one has to be very careful even in such a proof case to state that a protocol is secure? Or you never know exactly what the rules are. I've seen many examples of protocols that have been proved to be secure and then later somebody could throw them. But of course, there was different assumptions that we were using to follow the
Well, yeah, this is a problem with formal proof in general. You are always validating a certain model, and then the question is whether the model fits the real world. And I see one key research area, a very difficult one, is that one would like to layer the different proofs so that you would prove a protocol at an abstract layer, and then the next level down, you're getting closer to the bit level, you would then want to perhaps talk about using certain algorithms and prove that those algorithms are correct, and you would like to just glue those proofs together rather than having to do one giant proof at the bit level about everything, because that is just infeasible. But it isn't just a matter of gluing them together, because the interactions can be very complicated.
Right, I'll check that for protocol. All it says is good. If you use your method, it says yes, it's good, this is why. To my mind, what we're really using this for is how to debug protocols. And when you apply a model checker to a bad protocol, you come back, as I understand it, and say this is bad because you can reach this reachable bad state by such and such a path. That's useful to help you gain your protocol, whereas if you try and prove it, you find you can't. Because you find you can't, I mean, you don't get so much feedback for why you can't.
Well, firstly, model checking is good for debugging protocols, which is why I said these are complementary methods, and so you should use model checking for debugging. Although, in fact, with this method, if you can't prove it, often you can see in the thing that you can't prove, you'll be staring at a scenario which defeats the protocol. Actually, that happened to me once, so I actually discovered an attack in that way. Although model checking is probably a quicker way of finding attacks. The point is, though, merely to know that there are no attacks under some particular framework isn't necessarily all that you might want to know about a protocol. I recall proving some rather obscure thing, which I think it would be to go into details here would be going too far, but I don't think one could even express this property in model checking frameworks I've seen, but one can prove it, and the chains of reasoning needed to prove it are actually quite interesting in themselves. As I said, the proof tells you why. Model checking says it's okay. Once it's debugged, if you want to know more, then a proof will give you an argument. That's the point.